Hi everyone, I'm Chris and welcome back to the lecture on logistic regression of this machine learning course. This final section of the lecture is about the model evaluation with respect to the classification task. Let's take a look on an example to understand the challenges of evaluating classification models. In this example, we examine how many people have COVID-19 in a given dataset and for a model prediction. Our dataset has observations of 50 people. 2 of these 50 people have COVID-19. These 2 people are called true positive. They are highlighted in green. So, in our example, 4% of the people are true positive. The other people are negative for COVID-19. So 96% are true negative with respect to our data. We have 2 classes, positive and negative. A model which predicts always negative for COVID-19 has an accuracy of 96% to predict the correct class. So its accuracy is pretty high. But it is completely useless because the model will never distinguish between the 2 classes. The reason for the high accuracy is that the distributions of the 2 classes are very uneven. We have a lot of negative samples and only a very few positive samples. So, how can we evaluate the classification model? The idea is to evaluate the groups separately. On the left hand, the ground truth of the data is displayed with 2 people which have a disease and 48 without. On the top, the model prediction is shown. In our example, our model predicts for 3 people a disease. The ground truth and the model prediction can be compared in a table called confusion matrix. The first entry gives the number of people who don't have a disease in accord with the model prediction. So from the perspective of the model, they are true to be negative. For our example, 46 people are true negative. On the other hand, one of the people who are sick are identified as such by the model. So from the perspective of the model, this is a true positive identified person. Next, we take a look on the misclassified people. First, here are people without a disease, but the model falsely predicted one. For our example, there are 2 people where the model is false positive. Second, we have a single person which has a disease, but it was overlooked by the model. So the model was false negative. In total, the confusion matrix gives an overview of the model classifications in comparison to the ground truth. Normally, you have to find a trade-off between false positives and false negatives. Let's reconsider the logistic regression model with another example. The 2 classes, negative and positive, are encoded by a single target variable y. For y is equal to 0, we have the negative class. So negative data samples are displayed on the x-axis. For y is equal to 1, we have the positive class. The positive data samples are displayed as well. The logistic regression model fits an S-shaped curve the logistic function, to the data. We need a threshold to decide between the classes. In the previous section, we choose a value of 0.5. So all values of the logistic function below 0.5 correspond to the negative class. All values of the logistic function greater than 0.5 are predicted as positive by the model. So the input space is divided into two halves. On the one side, the model predicts a negative class. On the other side, it predicts a positive class. The separating line is a so-called decision boundary. The data points on the upper left are estimated as negative by the model. However, they are at y equals 1, so the data points are positive. Consequently, the model is false negative. On the lower right, we have model predictions which are positive. However, the data is in the negative class because y equals 0. Consequently, the model is false positive. If you are testing for a disease, you might deal more easily with false positives. If someone is false negative, the disease can be more easily spreaded because the disease remains undetected. Now the question is, can we find a logistic regression model which favors false positives over false negatives? We can adjust the decision boundary. Therefore, we choose a different value of the logistic function at which we choose a different class. Here, we selected this value close to 1 as represented by the green dashed line. So, the corresponding decision boundary moved to the right. On the upper right, the corresponding confusion matrix is displayed. By just taking the decision boundary close to y is equal to 1, we avoid false positive predictions. Everything on the right side of the gray line is predicted as positive. However, we have 3 positive data points on the left side of the gray line which are classified as negative. These 3 data points are false negative. The 4 negative data points are classified correctly. Now let's shift the decision boundary closer to the left. So only a single data point is on the left side of the gray line. This one is correctly classified as negative. However, now we have 3 negative data points classified as positive. So we have 3 false positives. All positive data points are now correctly identified by the model. By adjusting the decision boundary, you can get very different model predictions. You have to find the right trade-off for your needs. A model which always predicts positive will have a lot of false positives but no false negatives. On the other hand, a model which always predicts negative will have a lot of false negatives. To find the trade-off, different measures of model quality can be introduced. The first one is the recall. It evaluates the model quality from the perspective of the positive data points. It answers the question, how many of all positive data points are identified by the model? So the true positives are related to the sum of true positive and false negative. For our simple example, half of the positive data is predicted correctly by the model. Just looking at the recall score is not enough because it prefers models which are always positive. So additionally, we need to consider the model quality from the perspective of the positive model predictions. This leads to the model's precision. It is defined by the true positives over the true positives plus false positives. The precision answers the question, how many of the positive model predictions are really positive? For our simple example, the precision is 33%. So typically, we want to find a model which balances the recall and the precision. On the one hand, the ability of identifying positive data points. On the other hand, to be precise in its positive predictions. For different values for the decision boundary, we get different combinations of precision and recall. This can be plotted as a curve, the so-called PrecisionRecall curve. This curve is sketched on the right side. A model with large precision and small recall can lead to a model where all positive model predictions are indeed positive. However, usually many positive data points are not identified by the model. A model with small precision and large recall has many false positives. But the model identifies all positive data points. So, depending on your needs, you can choose a model on the curve. Besides the PrecisionRecall curve, there is another popular curve representing this trade-off, the so-called receiver operating characteristic. Here, instead of the precision, the false positive rate is plotted against the recall. The false positive rate is the ratio of false positive model classifications over all negative data points. So it answers the question, how many of all negative samples are classified as positive by the model? Plotting the recall against the false positive rate gives the receiver operating characteristic. On the left side, the curve represents a model which is mostly negative. On the upper right side of the curve, the model is mostly positive. So you can use the PrecisionRecall curve and the receiver operating characteristic to choose your model. Section finished and lecture finished. This lecture was about the logistic regression model for the classification task. Logistic regression fits the logistic function to data with two classes. We introduced the cross-entropy function to measure the quality of the fit. Then, this model was generalized to multiple class classification problems. The so-called Softmax regression was obtained. We examined the properties of cross-entropy and why it is preferred over mean-squared error. The cross-entropy cost function can be interpreted by the information difference of model and ground truth. Last but not least, we learned how to evaluate classification models. In the next lecture, we consider another algorithm for classification, the support vector machine. Thank you very much for listening. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next lecture.